Okay, let's begin. My name is David Wagner, and I am going to talk today about incorporating using anybody software for ergonomic analysis, particularly focusing on motion dynamics versus static analysis, traditionally used. I'd like to introduce the presenters. That's me on the left, Dave Wagner. The host of this webcast is Arnie Cliff, and one of the panelists is John Rasmussen. Before we begin, it's probably good to introduce you to the Q&A panel. If you click in the lower right-hand corner of your screen, the Q&A panel will open up, and you can type questions to the panelists, and at which point they will, depending on the nature of the question, forward it either on to me or answer it themselves, as they are the anybody experts, and I will get the questions that pertain to this presentation. Once again, it is important that you select, when you send a question, and select host, presenter, and panelist in the bottom right-hand corner versus just host or presenter or host and presenter to make sure it gets to all of us and we can answer your question. Once again, question and answers. I encourage everyone to ask questions as I'm going through the presentation, at which point it's probably easier for me to answer the questions through this format versus waiting to the end, although I do encourage questions also at the end. A little bit about myself. I am a PhD candidate at the University of Michigan, hopefully finishing up this December. So if anyone has a job opening or position they're willing to offer me, please do so. I work in the HumoSim lab, standing for Human Motion Simulation Laboratory, under the direction of Don Chaffin and Matt Reed. I encourage everyone to go to the HumoSim website at www.humosim.com, and or if you would like to know a little bit more about myself and the research that I do, you can go to unix.edu/DW Wagner. My work focuses, my PhD research focuses on the stepping behaviors and lower extremity motion that people use in work cell stepping transfer tasks, and particularly predicting those motions, and then motion simulation in general. This work, I'll get to this work later. So for those of you that can hear me, you can ignore me right now. I just want to put this up for the last few stragglers coming in, trying to get their sound working. So we shall just sit here for a little bit while we make this last few final technical adjustments. Okay, that should do it. For those of you that can't hear me, I hope you get on board quickly and set it up as quick as possible. So this presentation in general is not particularly about my PhD research, but it is more of an exercise that I thought was important, which is addressing the why am I doing this section of the presentation. And I have noticed over my PhD career that the field of ergonomics, at least in its application, and the field in the research realm are sometimes at a disconnect. And with the advent of computational ergonomics or computational biomechanics, particularly the anybody software, I felt it was would be an interesting exercise to see what the new benefits that this software provides over the current available software, and then also what could I gain from it, how long would it take me to set this up from the perspective of an ergonomist, and try to bridge the gap between application and research. So some of the questions I would like to address today are, one, there are current human figure models that are used for ergonomics, and how are they used, and how do they differ from the anybody software. Number two, why doesn't everyone perform full dynamic analysis, and why are most of the ergonomic analyses done right now in the static or quasi-static realm? And then a couple points about the any-body model that we use in our modeling and analysis, some results with regards to the load back, compression and disc forces, with regards to some lifting tasks, and then summing it up with some what did I learn, and is this process feasible, and would I definitely recommend it for other people to take on. For those of you that would like to get a little bit more information with regards to what is being presented here, this work was presented in a little different form at the SAE Digital Human Modeling Conference this past year, and the paper was published with myself, John Rasmussen, and Matt Reed. And I'm going to present it in a little different format here, but most of the information that I'm presenting today was published in the proceedings here. So I encourage everyone to download this, and hopefully soon I'll be able to get this paper up on my website if you are also interested, and possibly John may have a copy for distribution. So back to the question at hand, what are the current uses of the human figure models that are used for ergonomic analysis in application in industry today? And once again, I'm not an ergonomist expert or anything, but this is what I've learned throughout the time that I've been using the digital human models and the research that I have come across. They are very helpful in scoping out anthropometry, range of motion, that I can posture these digital human mannequins, and the ones I'm referring to, the commercial software, are the that I'm familiar with, are the Jack mannequin or the Delmia Katia V5 mannequin that are pictured here below, and how traditional ergonomic analysis works, at least how I'm familiar with it with regard to these mannequins, is that you can posture these mannequins in a geometric environment like the one Jack in the bottom left-hand corner here in the truck cab. And then you can perform reach vision capability. You can posture them in a way such as this, applying forces or loads to the different extremities, and calculating joint moments, possibly percent strength capable with regard to the programs out there, the University of Michigan 3D Static Strength Prediction Program, 3D SSPP, and then possibly also joint forces, low back compression, and such. And one of the key factors that goes into these digital human models when you're performing ergonomic analysis is usually you must have a posture or a representation of the human figure model before you're able to do analysis. And usually the posture directly affects the results, as to be expected. And one of the issues, and we're going to come back to this with regards to this analysis, is that there are at least three very general ways to capture posture or get posture into these mannequins. And one is just a simple feasible approach. Can I articulate the mannequin with some given joint constraints and put them in a posture to feasibly perform a task? Usually this is an ad hoc method, but fairly easy to do. However, usually in terms of ergonomic analysis, the feasible posture or the set of feasible postures is quite large, and what an ergonomist would rather prefer is the posture representative of an actual working population, and that sometimes can be simulated, sometimes can't, and so traditionally people will fall back onto the motion capture realm, which sometimes is cost prohibitive and also difficult to manage at times. But so these are three realms, and the realm that I generally work in is a simulated representative posture, which is what the Humelson lab is generally going towards, the motion prediction or posture prediction algorithms. So before I get too far into this presentation, I would like to once again point out the question and answer panel in the lower right-hand corner. If you'd like to ask questions, if you'd like to answer questions, you can go ahead and do that too. But if you'd like to ask them and have me answer them or one of the panelists, make sure you select the host, presenter, and panelist when you're typing a question, or else it might not get to us. So what is the premise of the study? I've introduced visual human models, and and what do I want to do now with this anybody software? Well, as an ergonomist, I traditionally use these visual human models, and I would like to assess what can I do as an ergonomist with the capability of dynamic analysis, like that performed by the anybody modeling software. And I'd like to answer questions such as, is it helpful? And really, is it helpful with respect to the the dynamic analysis over the static analysis? And does it provide me any additional information? Do I have all the necessary information to run this analysis? Do I have to collect more? Can I just use the information that I normally use for static analysis with this new fancy dynamic analysis? And then what are the potential time-benefit trade-offs? Does it take the same time to set up, or do I have to go through quite a bit of setup and tweaking to make this potentially work? And some of the guidelines before I get started is that before I got started on this project is that I wanted to, as an ergonomist, wanted to use as many predefined models as available to me versus writing custom code, developing custom models, because as an ergonomist, I may not have time to do that, and I would like to use the software already available that has been hopefully validated and can be used as a commercially great tool to make decisions. And then subsequent to that, I would also like to keep models generic that I do develop, because I know I'm going to have to do analyses like this, similar to what I've come up with in the future, because that's what we do in our job, and I would like to be able to use the analysis that I've developed here, sort of tweak those models and move forward with new, potentially different tasks. So before I get started, I would like to familiarize everyone with the single trial I am going to analyze here, just so we're on the same page. And what we're going to go through here is I'm going to analyze lifting tasks, and I'm going to analyze that lifting task through an ergonomic perspective with the anybody modeling software, and I'm going to compare the static analysis that is derived from the anybody software with the dynamic analysis that is derived from the anybody software with respect to some joint moments and low back loading. And the task that I selected to analyze happens to be a two-handed lifting task where an individual starts with a position over here, approaches a two-handed load which weighs 4.54 kilograms, lifts the load however they wanted, so the self-selected posture, turned around to a 135 degree angle and deposit the load off a few steps away. And we're really going to analyze this numbers 2 and 3, these portions, and we have some custom force plates here to be able to apply some ground reaction forces to our antibody mannequin when we eventually get that point. So now that we know what I'm going to try to analyze, taking a step back and looking at sort of addressing the question, why doesn't everyone use dynamic analysis all the time? There must be something that I've missed here that I haven't quite put forth, and that is summed up in this slide here. That the advantage of the dynamic analysis over static computations depend on the task characteristics, which are at times ambiguous. There is no quantitative criteria, sort of an acceleration limit, maximum momentum to guide the selection of dynamic over static analysis. And it's not really intuitive. And I know from my own experiences that possibly if I were to analyze someone throwing a baseball fairly fast, a baseball pitch, that I'd probably use dynamic analysis. But then at what point does that transition between a dynamic analysis that is readily required to static analysis being sufficient? So once again, this assessing the validity of the static assumption is sort of left up to the ergonomist, which is my role in this task. And and then subsequently, most of the tools available to me that perform ergonomic analysis don't even have the capability to perform dynamic analysis, including Jack and SafeWork, although they do a very good job at what they do. However, they've selected to not include those types of capabilities. And I've included a simple flow diagram of what I think I'm going to need to make dynamic analysis happen and some potential barriers that might come up later on. And that is body motion, very similar to what I may need for the quasi-static analysis that I may do normally. Body segment parameters, this may be a little bit more in-depth than what I'm used to, but still, I probably collect those if I'm going to analyze a single person doing a single task. And then some of the potential barriers that I foresee are, well, one, I've already talked about this, availability of inverse dynamic software for use with ergonomics. It may not be readily available, although I hope to solve that with the use of this Anybody software that I've just acquired. And then once I am able to generate some numbers and run things through, what's going to be some joint level criteria that is going to allow me to judge is this job safe or not safe, and maybe I'll find that in the literature, or maybe I'll just have to come up with some best guess scenarios. So some people have looked at this problem specifically with regards to lifting previously, and they've compared static and dynamic lumbar motion. And these plots are from, I believe, McGill and Norman, and it's just an overlay plot of the static versus dynamic lumbar moment from a sagittal plane lifting model that predicted these lumbar moments. And qualitatively, it looks like the dynamic lumbar moment peaks at higher values than the static lumbar moment, which would sort of go along with our belief in this dynamic world. That makes sense. And the underlying assumption that comes from these papers is that the dynamic lumbar moment, or rather the dynamic analysis, is more representative of what the body feels and what's going on internally with the body versus the static analysis alone. However, again, they do state here that it is difficult for an ergonomist or at least I say, it's difficult for an ergonomist to determine, simply even with these plots, whether or not dynamic analysis needs to be performed, or if I can simply rely on the tools that I have available to me and static analysis will suffice. So once again, I've talked a little bit about the static analysis, quasi-static analysis, and then potentially dynamic analysis. There's even some others in here, quasi-dynamic analysis, which I'm going to ignore right now. But this is just a graph of a table of what I mean by that. Static analysis is I am taking a single posture from a mannequin, I'm applying forces to that mannequin, and I am calculating joint moments, low back compression from that single posture. And essentially the inertias, well, there are no inertias because there's no moment, but that same analysis can be applied over a sequence of postures, essentially motion, and the assumption here is that the inertial effects are neglected because I'm essentially just taking a snapshot in time and applying that static analysis at each plane in time if I do happen to have a motion from motion capture data, for example. And what I would like to try and attempt to do here is this full dynamic analysis where we have realistic representation of changing velocity and acceleration profiles of body segments, and the input, once again, is this motion along with a well-scaled mannequin to the properties of the person I'm analyzing. Although this is the big issue here, the motion being realistic and, at least in terms of numerical accuracy, representative in terms of velocity and acceleration profiles and not being numerically inaccurate. So our any-body model that we use, or that I use, started from the free posture move model, and the goal, for this study was to attempt to use as many predefined models as possible, and that started with using a whole body model and driving that free posture move model with angular data, which is how it's defined in an open repository on the Anybody website. And each of the, I think there's 42 degrees of freedom, not exactly sure on that one, and each of those degrees of freedom has an angle associated with it, except for the global XYZ position of the pelvis, which gets held in place. All the other lengths have angles, and we, as you saw previously, we did have motion capture data for that one trial, and the process went something along the lines of we capture the motion capture data with regards to marker data. We use that marker data to reconstruct joint center locations, and that's just what we do in-house, at least in our laboratory. And then from that joint center location data, we would like to drive the any-body model. One of the nice things about the free posture move model was that the online, the open repository, and that I can look at the code and I can derive how the angles for each of the body segments were calculated. As you know, the Euler angles, or potentially the Euler angles are not a singular case, so there are multiple solutions for a given set of rotation matrix. And so, but you can look on the Anybody website, or rather inside the model, and sort of backwards calculate how they're getting those angles. And from that, we were able to calculate those same angles and how the Anybody model is driven with our joint center location data. Long story short, that did not work so well because we knew later on we were going to have to apply forces at the feet, and we knew that and also at the hands, but the feet were the main problems, and we knew that those forces had to coincide with the center of pressure data that we calculated from our force plates, and with the angular data, the resolution just simply was not good enough to make everything really work well. And so we ended up changing some of the angular data to positional constraints with regards to the joint centers that we had, and do that sort of at an incremental process just to make sure the model was continually always able to run and not kinematically indeterminate or possibly kinematically infeasible, and which sort of provided us a method for changing the model and developing our own. Also on lines of model performance, we know that we have an individual that we collected data from, and the Anybody mannequin requires that there be some type of body mass distribution applied to the bones. And in an attempt to get the most accurate data possible with the change off of being clinically feasible and possibly easy for me as an ergonomist to accomplish, we reviewed the literature and found a clinical study where they estimated the masses of different segments of the body with laying an individual on a force plate, so the force plate here supporting this individual, and having the individual change the position of a single segment of the body. And if you measure the change in displacement of the center of mass of that segment, along with the change in center of pressure, you can calculate the mass of that segment. Unfortunately, that didn't, again, prove to be adequate for the Anybody model because we simply couldn't get the fidelity that we needed with respect to all the mass segments that the Anybody model required. As we expected, this technique is really only good for the extremities. Even the head was very difficult because you simply just cannot move the head very much with respect to in keeping the rest of the body in the same place. And so right now I'm only presenting these numbers as sort of validation numbers. So we measured the shank and foot and the lower hand and lower arm compared to the 50th percentile mid-male scaling that anybody supplied. These are our values, and definitely there was no way we're going to be able to calculate the vast distribution of the spine for the different lumbar, thoracic, and cervical regions. So we ended up falling back on using the scaling techniques of the mid-sized male and simply applying the mass of our individual with respect to those values. Once again, to follow up on the anthropometric scaling of the model in terms of the geometric scaling, we again use the predefined values from the any and any Jack files that are available that have predefined scaling metrics in them. And initially started with that, plugged our values in that we measured from traditional anthropometric measurements, and attempted to scale the model initially that way using the uniform scaling versus one of the more fancier scaling by body mass percent weight, simply because we did have the measurements of each of these joint center to joint centers, so there's no reason why not to use them. A couple problems that we had while we were doing this was there was no value for trunk width, and which unfortunately was scaled, I believe, as a percentage of trunk height for the scaling uniform, and we had to add that in simply because the shoulders of our individual may have been broader, and so when we applied the glenohumeral joint center to track for that position, we needed it to be fairly accurate, unless we would get, and if it wasn't, we would get protraction, elevation, angle problems of the shoulder, and we didn't want to deal with that. So scaling the trunk width was important. And again, we also had trunk height issues where our trunk height was significantly shorter than the any-body model was requiring. So we ended up using a residual stature metric where we knew the height of our individual, measure the height of the any-body mannequin, and after scaling everything else, we matched the trunk height to make sure we achieved a stature appropriate for the any-body mannequin. It would have been nice if there was some, there was a couple ways we could have made this a little bit better. We could have written our own scaling uniform measures. There wouldn't have been any problem with that. However, as the premise of the study is that I don't want to write very much custom code, so with that, I probably took a shortcut here and just left it as is, and the model did run and was kinematically feasible throughout the whole trial, and that was sort of good enough for us. On to the model kinetics and environment reactions. The free posture move model is structured as such here, where the pelvis is fixed in place or by some positional constraints. And which leaves open chains for the torso and the two legs. The forces that were applied at the feet were only applied at the feet for when the person was standing on the force plate, essentially when we had center of pressure data. So for all other times when the foot was not on the force plate, the only forces that were applied here were due to the inertial effects and just the mass of the leg due to gravity, instead of supporting the complete body weight of the mannequin. The application of applying the center of pressure to the different feet was taken from the any gait model that was previously developed, and the lifting of the box was handled through a conditional constraint in which there was two box handles and the grip center, and as the Euclidean distance between those grew smaller at a certain time, when it grew to the smallest possible, or rather a particular criteria, the box would be lifted, and then the weight of the box would be supported by the mannequin, where previously it would be supported by the shelf. And this was performed, this type of conditional constraint was taken from any 3D a 3D lifting analysis that was done on the Anybody website. So again, another model that we cribbed and put into our own. And this worked pretty well. And how we did this was we ran the model first without the box motion in just kinematic analysis, and we tracked the grip centers of the hands, and then we used those grip centers along with information about when we knew the box was picked up through data from the experiment, and drove the box with the grip centers of the hand data. So then we knew that we would be able to grab the box, and the model would be able to follow appropriately. Here is pictures of the model as best I can using the full muscle model available in Anybody. It starts over here, moves off this way. And as you can see, these frames occur over 0.2 seconds, and one sort of interesting thing is this individual selected a single limb stance to pick up the box, which is something that as an ergonomist we usually don't see in terms of the analysis that is performed. We see it all the time out in plant data when people are walking around and throwing loads around, but in terms of the digital human mannequins, when people usually perform analysis, they usually bring the 2 feet real close to the object, bring the hands close to the object, and lift the load in a parallel stance. And this is sort of neat that potentially dynamic, and potentially, not to give it away, but potentially a dynamic analysis would be more appropriate here because, well, we're standing on one leg. There's definitely motion as the person's picking up the box. So I think we may be heading in the right direction here. Some of the results here are, and let me just explain some of these graphs here. The pictures on the sides and the times here correspond to the postures and times at which the peak dynamic and peak static moments occurred. And these moments were taken using the no muscle model available in the Anybody framework. And these different plots, the blue lines are the dynamic moments, and the red lines are the static moments. And as we can, and the green line is when the individual actually picks up the box. And we can see that in all cases, although the times do not line up, and in every case, although we would not expect them to, the static analysis definitely underestimates the peak static moment, definitely underestimates the peak dynamic moment in all cases. How we accomplish the static versus dynamic analysis was the dynamic analysis was formed as already presented with the actual data in real time, not in real time, but in the actual time frame. However, the static analysis was performed essentially by stretching the time out by a factor of 1,000, attempting to negate any inertial effects. Some of the results related to the low back compression. Once again, we have the similar plots here, and again we have the percentages at which static analysis underestimates the peak dynamic forces. And in this case, the low back compression happened to occur at the same time for both analysis, and that occurred when the mannequin lifted the box off the shelf. And once again, these were low back forces predicted the L5 F1 joint, and the peak compression force of 1822 newtons versus for the dynamic analysis versus 1152 for the static analysis. Interestingly, the shear force for the static analysis occurred significantly farther in front of when the individual picked up the box, potentially associated with either numerical error, forces at the, or just a posture that was person is transitioning from, and at that static point, the shear force happened to be large, and I would probably call that an anomaly because the motion definitely more static, and so that's a tough one to judge right there, whether it's sort of a realistic force versus sort of not a made up force, but an inherited force from just a static analysis assumption. So one of the issues that we wanted to look at is, are our results similar to what other people in the literature have seen with their comparisons of dynamic and static lifting tasks? And the answer to that question is yes and no, depending on what you look at. Quite a few different studies have looked at this type of comparison, and I'm listing the underestimation here of peak dynamic flexion in the L5S1 joint, and our results were 40.7%, and other studies have listed significantly lower values, potentially due to the load weight, the constrained foot placement, where they force the person to stand in a parallel stance and twist from 90 degrees to 180 degree twist, which may induce artificial moments, because while our task was unconstrained and the individual was able to select their own personal way to perform the task and perform the lift. However, for one study, Song et al., where they investigated load weights very similar to ours, were in the same ballpark with 34.5 and 40.7%. Or rated a floor to waist lift, although ours was always a waist level. And again, one definite thing to note is that the peak low back compression for our analysis was 1822, and at least in the U.S., that would yield the same conclusion relative to the safe lifting criteria set by NIOSH, which is anything less than 3,400 Newton compression force gives us is okay to lift, versus over that is sort of a no good job needs to be redesigned type of task. So definitely the implication of this analysis is that the quasi-static analysis, however, the implication is that the quasi-static analysis may fail to identify some jobs that do exceed that criteria simply because of the large underestimation of the dynamic peak force that we're seeing here. So some parting thoughts in terms of what I went through in terms of kinematic modeling in the Anybody software. One issue up front, and this is being addressed right now by the Anybody software developers, and that's the kinematic redundancy must be handled at the software level and not by the user. It would be nice if this occurred, and unfortunately this is right now is not the case, but I know Michael Anderson of the Anybody team is addressing this and has presented a previous webcast, which I'm definitely excited about. And this just goes to the ease of handling dynamic analysis, that it probably wouldn't be feasible for an ergonomist to go in at this level and assign the degrees of freedom and the drivers of those degrees of freedom for each analysis. It would, again, be nice for predefined functions for model scaling. They were limited, and it would be nice if they were had a little bit more flexibility and capability to scale the body dimensions as I would have liked. Addressing that point again, it would be nice if the utilization of a publicized standard set of anthropometric parameters for whole body scaling, so it would definitely improve the overall model generality, as I think it would be more useful to some people that are possibly set in their ways with a particular anthropometric database, but it may be more appropriate in terms of expansion into other realms also. A couple nice things were the separate body and application repositories. It was very nice to be able to start with a predefined model where I didn't have to create something from scratch every time. And once again, to review the models that we used, we started off with the free posture move model. We applied the foot constraints, or the foot conditional contact from the gait model with the drive and the center of pressure forces. We applied the conditional contacts with hands using the predefined lifting model, and then we were able to use the predefined full body muscle and no muscle models to calculate the joint torques and joint low back forces. So again, that was definitely excellent. And the help provided by the Anthropometric team was also very beneficial. One thing that I see is that I didn't really use here and didn't discuss here, but that I've been using in the past couple months that I think has shown quite a bit of promise to pushing this software even to the next level, and that is the command line interface allows me to instead of running one analysis, which is great for an ergonomist, what I would really like to do is if I have a task and let's say I even have some simulated motion that accounts for the variability in the population, I would like to be able to run those motions through the Anybody software. And instead of one task being analyzed, I'd like to be able to do 100 or 500 with different body dimensions, different motion styles, and get the variability in terms of the low back compression, low back moments. That I think would be quite impressive. And I'm fortunate enough to have about 100 files of a similar lifting task with single-handed lifts and two-handed lifts where people actually step on the force plate. and I've been able to do this fairly easily using the Anybody, using some custom-written MATLAB software to write custom files to the custom any files where then I can call from the command line and run the kinematic analysis and then run the inverse dynamics analysis and then output all that data using the predefined output information and output that to files and then compare that across the board, which is kind of nice. I'm not going to talk about that, but if you want to talk about that, definitely shoot an email and we can talk further about that. I think that may be the way ergonomic analysis is going to go in the future. So what is the future of dynamic effects? We definitely saw that inertial effects do affect model estimates, much as the other authors that investigated this previously saw. Unfortunately, motion capture is the only way to generate these quantitatively realistic motions of sufficient quality for inverse dynamic analysis, although I think that is changing with the motion posture prediction models that are currently emerging in the field of ergonomics, and Humelson, the lab I'm part of, is developing a model that hopefully will be a part of that emerging field. Motion simulation software, again, must be improved to accommodate realism in not just posture, but also, again, the velocity and acceleration domains as well. That goes back to the point of getting realistic motion simulation. And so instead of relying on motion capture software, you can simulate the motions and get, again, similar or more reasonable results that way versus the sometimes cost prohibitive of motion capture equipment and running the software that way. Again, this work is not demonstrated that ergonomists are currently failing to diagnose dangerous jobs by not including dynamic effects. So that should definitely not be a point that is brought away. That this is from this talk that the ergonomists are doing their job, and this work definitely does not show that they are not in any way. Again, including dynamic effects and analysis tools will also only be helpful if the acceptability of tolerance criteria, such as the safe or not safe job criteria based on dynamic considerations, are further developed. And although we have this tool now that can predict, or not necessarily predict, but model the effects internally, what the joint moments are, without apps criteria of whether or not those predictions are safe or not safe, it may not apply. Although, without being able to calculate them, how can we, I must raise the point, how can we actually define criteria on them? So I think we're definitely heading in the right direction, because it's sort of the chicken versus the egg problem, that you need to be able to know what the values are before you can talk about them. For further information, I would definitely recommend users of the Anybody software, if you're looking to get involved, go to the top 3 websites listed here. The technical group of the Yahoo Yahoo Manuscript Group is very informative. The folks at Anybody Software answer those questions fairly quickly and are very helpful. If you'd like to know a little bit more about the Humanism website or myself, definitely feel free to go to those websites. Again, I'd like to thank you for listening, and a special thanks to my PhD advisors, Matt Reed and Don Chaffin here at the University of Michigan, Don Rasmussen, who helped with the technical problems that came up sometimes with developing the model, Arnie for making this all happen through the webcast, the Anybody panelists, and the Humanism partners who fund my research, consisting of the company logos listed here. So that is it for the technical portion. I would like to open it up for questions and hopefully answers by either me or the panelists.